Okay, welcome to video lecture 14. The first thing I'm going to ask you to do is pause the uh, lecture so you can look at this cartoon. Okay, so I'm assuming you're done reading the cartoon. I wanted to do here just a quick introduction of the basic concept of statistical significance before backing up just to look at the details about the underlying process of getting there. So this lecture sort of roughly corresponds to the material in Statistics Without Tears, starting on page 102. So if any of you are approaching this idea of statistical significance for the first time, um, you might have been chagrined or confused by articles you've maybe read recently or things that I have up on the Canvas site, articles that seem to pull the rug out from under this scientific gold standard of statistical significance, which is usually set at that 0.05 letter. To me, I feel like in teaching this class, it's important to make sure students understand that basically in science, just like in law, there are gray areas. Um, these articles that talk about statistical significance, and that it's not equivalent to a gold star seal of approval. They show that it's possible to cast doubt on scientific evidence, even evidence that does meet the classic gold standard of statistical significance at the 0.05 level. I mean, if you're contemplating doing litigation or doing even policy work, you need to understand that practical significance isn't necessarily tied to statistical significance, first of all. But then secondly, it's helpful to understand how to find potential weaknesses in scientific results that have reached statistical significance. All right, so a basic purpose of most scientific research is to determine the, quote, significance of some effect that is noted in a study or an experiment, or the significance of a relationship between two or more variables. Again, remember that statistical significance isn't about significance in any practical sense in the real world. Instead, it's just a mathematical way to interpret data and decide whether those data can be generalized to a population or to another place or time. Or it's a way to describe our confidence that there is a real difference between two populations of interest. Say, for example, in a study on the effects of a new medication, where one sample gets a placebo and one sample gets the active medication, you can use this math to describe your confidence that any difference you see is a real difference rather than some difference that happened purely due to chance. Okay, so this idea about whether something can be reliably and validly generalized is, again, usually referred to as statistical significance, or sometimes people just use the word significance, which can cause some confusion. So basically, researchers apply statistical theory and mathematical formulas to decide the likelihood that the difference seen in a particular study could have occurred by chance. So it's all about answering this question. If we see a difference between samples, right, do those differences reflect true differences between the populations of interest, or do they just reflect random variation between our samples that could have happened by chance? So another way of putting this, when we're talking about using samples to do a study that we want to generalize to a population, is this. So let's say we observe in our study that there's a difference between two samples, one of which is a control sample, the other of which is a sample we've subjected to some experimental condition, and we see a difference between our samples, right? But the next question you have to ask as a researcher is, well, how likely is it that the differences we're seeing reflect true differences between our populations of interest? Because the concern is always that the differences we have seen might just reflect random variation between the samples that could have happened by chance. So I like these diagrams because they show three different scenarios, three different possible sets of data that could reflect the results of a study. So let's imagine it's a study of a new headache medication for migraine sufferers. And these diagrams show three possible results of our study comparing a placebo pill to the new medication. So let's imagine that we had our study groups and we asked study subjects to wait till they have a migraine, then take our pill and rank how much relief they got after taking the pill, from 0 being no relief at all to 20 being complete relief, okay? Now in each of these scenarios, the green curves show the relief scores from people taking the placebo pill, and the blue curves are the results of people taking the active medication. So I want you to notice that the means in each of the green groups, right, the means in each of our three possible scenarios in our green groups are the same, and the means in our blue groups are the same, okay? So in each of these scenarios, the mean level of relief is higher in the experimental group than in the placebo group. But I think right away, especially after reading Statistics Without Tears, we can see that this data set down here is going to give us the most confidence that our new pill actually works better than a placebo. And why is that? Well, the troubling area that we're worried about is this area of overlap, largest here, right? So we probably have the least confidence with this group, maybe a little more confidence in this group, and then the most confidence here. Because if there's this much overlap in the group, we can actually imagine that, you know, wow, people in the placebo group could be getting relief for no reason or a random reason. But if we have this much overlap, there could be a lot of people in our actual experimental group that are getting relief for no reason or a random reason. But down here, when we see very little overlap, we see a much more stark difference. So we think there's a better chance that the difference is due to the real effect of the new medication. So the differences that we see in these three diagrams, they're reflecting not just the means of each group, right? But they're reflecting the dispersion, the variance. And it's a great illustration why both the mean and the dispersion always get taken into account in those formulas for calculation of statistical significance. So you should review pages 122 and 123 in Statistics Without Tears to remind yourself that while there are ways to do significance testing on sets of samples that have the same mean but different distributions, or on samples that have different means and different distributions, right? We're not covering those in this class, right? The methods we're talking about only work with samples that have different means but similar distributions. Okay, one important thing to remember is in any study, you always start with your null hypothesis, right? Null hypothesis is that there's no difference between your two populations. So in our study, looking at that prison program's effect on recidivism that's in the Monahan and Walker book, the null hypothesis would be that the program has no effect on recidivism. And in our study of our new medication versus a placebo, the null hypothesis would be that the medication has no more actual effect than a placebo. And then, of course, your alternative hypothesis is what you're measuring to try to falsify. So in these two examples, the alternative hypothesis would be that the prison program does reduce recidivism, or that the drug has a positive effect on a particular illness or condition beyond that of a placebo. So, as a scientist, after stating your null hypothesis, then you gather your sample data, and then the data are entered into a mathematical formula to calculate statistical significance. And this is usually done all by computer now rather than in the past with slide rules and such. And the most common cutoff used is the 0.05 or 5% number, and this is often referred to as the p-value of 0.05. So the Statistics Without Tears book doesn't use the term p-value much, but you're going to see that a lot when you come across scientific information. So it's always good to know that p-value just means the level of statistical significance attained by the data. All right, and then assuming the null hypothesis is true, the p-value is defined as the probability of obtaining a result at least as extreme as the one that was actually observed. Okay? And really, the level of statistical significance that needs to be attained before discarding the null hypothesis is chosen by the researcher. So if we want to use this commonly used p-value of 0.05, for example, we're only going to reject our null hypothesis if the mathematical significance test shows that the observed result would be expected to occur by chance no more than 5% of the time. So again, the p-value is actually chosen in advance in terms of how much significance you're going to require before you reject your null hypothesis. And even though the commonly used cutoff is 0.05, some studies will use a stricter p-value cutoff like 0.01. You know, the point, it's so interesting to look back and see where this 0.05 number came from. We have Ronald Fisher, our mathematician, whose original interest was agriculture, right? He wanted to test whether variation in crop yields was due to some specific intervention, like fertilizer, or merely reflected random factors beyond experimental control. So first, he assumed in his field that the fertilizer caused no difference, the no effect or null hypothesis. And then he came up with a formula for calculating the number we now know as p-value, the probability that an observed yield in a fertilized field would occur if the fertilizer had had no real effect. So the story goes that Fisher basically arbitrarily declared that if p is less than 0.05, meaning that the chances of a random result being, you know, that your results occurring due to random chance is less than 5%, then that result should be declared quote unquote statistically significant. And then you can reject your null hypothesis, right? In his case, confirming that fertilizer works. Probably he did this because of the slide rule convenience, and that that was an easier number to compute. But Fisher's p-value 0.05 has become the benchmark of validity and credibility for all kinds of science. This is the most common number that gets zeroed in on, most commonly used cutoff. So you're going to see results of every scientific study or experiment reported with a level of statistical significance. So a researcher is obviously going to report a lower p-value if the data reflect that. So even if she set out looking for at least a 0.05 level, if the results are actually more dramatic than that and she can get a lower p-value, she's going to report that, right? Because remember, the lower the p-value, the less likely you'd get your study results by chance, and therefore the lower the p-value, the more statistically significant your result is. Okay, so just one more time, just to make sure we're all on the same page. If we're using this common p-value cutoff of 0.05, we can say this: if the odds of getting a difference as big as the one you found, if there were really no differences between the populations, are 5% or less, you then will reject your null hypothesis and accept your alternative hypothesis and say that your data indicate that a statistically significant difference exists to the 0.05 level, right? And on the other hand, if the odds were more than 5 in 100 that you could have gotten your chances by chance other than any real difference rather than a real difference, now you're going to fail to reject your null hypothesis because you'd say you can't conclude, at least from this study, that there is a real difference between the two populations. So here are words that you'll commonly see to describe different significance cutoffs, right? If something attains 0.05, it'll be described as being statistically significant. If the p-value, though attained, is better, in other words, is smaller, like a p-value of 0.01 is sometimes described as being highly statistically significant, and then a p-value of 0.001 is sometimes described as being very highly statistically significant. But a lot of times the word statistically is left out of those statements, and that's why statements about statistical significance in the popular media often get misunderstood, right? They'll say a significant difference was shown, even if it could be a very small difference with a large sample size. Yet an average reader who doesn't know that that word significant is a statistical term rather than the usual definition of that adjective might overvalue the results of that study. Here's a classic nerdy scientist t-shirt, right? Okay, one more time. You always start by assuming your null hypothesis is true, and then your p-value is the probability of obtaining a result at least as extreme as the one that you got. I'd like you to take a look at this. This is another one of my favorite cartoons from XKCD that illustrates the way scientific results sometimes get reported and sensationalized. So go ahead and just scroll through, pause the video and just scroll through until you read the entire cartoon. So this particular part of this slide here is something that I want you to pay attention to, because this is an error in logic, the transposed conditional. You're going to see this mistake made in the popular media. This mistake is made even in books about science. It is definitely mentioned a couple of times in various articles that are uploaded for your reading. I think it's one of the trickiest concepts that we cover, but I have some examples to try to help us wrap our brains around it. Okay, so let's talk about transposed conditional. So Transposing the conditional is the mistake of thinking that statistical significance at the 0.05 level means that it's 95% certain that the observed difference between the experimental groups or sets of samples is real and could not have risen by chance. Because even if you've calculated that the chance of a fluke or random result is less than 5%, you still have two possible conclusions. There is a real effect, or the result was due to chance, right? In fact, if you think about it, if a study finds no statistically significant effect, that's not absolute proof of anything either, right? Maybe the effect doesn't exist, but maybe your statistical test just wasn't powerful enough to detect a small but real effect. Certainly that can happen with smaller sample sizes, among other reasons. So once again, statistical significance at the 0.05 level does not mean that it is 95% certain that your particular observed differences is real and couldn't have arisen by chance. So another way of defining the transposed conditional is to say that the probability of getting your experimental result, if you were to assume the null hypothesis is true, is not equal to the probability of the null hypothesis being false given your experimental results, right? So the first half of that sentence is basically just the definition of statistical significance, right? I mean, a 0.05 level of statistical significance means that there's a 5% or less chance of getting your result merely by chance. And it is very important that you include there that you're assuming that the null hypothesis is true. That's a critical part of the definition. But that doesn't allow you to then say that there's a 95% chance that your result is real and that your alternative hypothesis is true. Or in other words, a 95% chance that the null hypothesis is false. So here's a great example that I think is one of the easiest to understand. So the probability that a person is a lawyer, given that she's a Supreme Court justice, is not the same as the probability that a person is a Supreme Court justice, given that she's a lawyer. That's just kind of an illustration of transposing the conditional that I think we can all understand. And then I can't remember if I'm actually going to require you to read this Science News piece entitled Odds Are It's Wrong, but I will have it uploaded on Canvas. So it's an example from this article. So suppose a certain dog is known that when this dog is hungry, it barks constantly. Constantly barks when he's hungry, but when he's well fed, he barks less than 5% of the time. Still might bark when he's not hungry, but less than 5% of the time. Okay, so in this example, if we, assume that our null hypothesis is that the dog is not hungry, the probability of observing the dog barking is less than 5%. Okay, if we assume the null hypothesis that the dog is not hungry, we know the probability of seeing him bark is less than 5%. Okay, so now we see the dog barking. What is the likelihood that the null hypothesis is incorrect and the dog is in fact hungry? So here it is illustrated with a golden retriever. So the null hypothesis is our dog is not hungry. We see, right? Because when the dog is hungry, it barks 100% of the time. When it's not hungry, it only barks less than 5% of the time. We see the dog barking. Here's our question. What is the likelihood that the null hypothesis is incorrect and the dog is in fact hungry? And the answer is not 95%, right? The answer is we actually can't calculate that probability with the information that we have. So as that article points out, a well-fed dog, sure, might rarely bark, right? It barks 5% or less of the time, as opposed to barking constantly when hungry. But just seeing the dog barking doesn't necessarily imply that the dog is hungry, because we know the same dog might bark 5% of the time even if he's well fed. And so from the information given in that hypothetical, we really have no idea what the chances are. He could be barking for any number of other reasons. So seeing the result that the dog is barking still leaves you with two possibilities. He's hungry or he's not. So actually, to even start calculating the actual likelihood of him being hungry when we see a bark, we'd need to know a whole bunch of other things, right? How often the dog is fed, and you'd probably have to use Bayesian statistics, which we are not going to go into in this class. The transposed conditional concept also comes up in DNA profiling. Remember, our random match probability definition in DNA profiling is the probability that a randomly selected unrelated individual in the general population or some part of it would have the particular DNA profile found in a crime scene sample, right? An example here, the random match probability of 1 in a million. So early on, when DNA evidence was first being used, prosecutors were making this error, now referred to as the prosecutor's fallacy, by saying in court something like, oh, the chances of anyone other than this defendant committing the crime are 1 in a million, or the odds of the defendant's guilt are 1,000,000 to 1, and so on. This mistake was made quite commonly, even though people tried to explain this to prosecutors. It was really only when these cases started being reversed for this error that prosecutors wised up. I mean, very occasionally it will still happen in court, although quite rare. But it certainly does happen in the media, in media articles describing criminal cases using DNA. Okay, this is the end of video lecture 14.